Hello, my name is Joshua Kraft, and I am the team lead for this project, majoring in chemical engineering, and am responsible for the removal of heavy metals through ion exchange.
My name is Evan Anderson, the team facilitator for this project and a chemical engineering major. I am also the lead for the demineralization of water through ion exchange.
Hi, my name is Cole Stickland, and I'm a chemical engineering student at the University of Arizona. For this project, I was responsible for the design and analysis of the reverse osmosis, or RO unit.
My name is Quinlan Nollgrass. I am majoring in environmental engineering and am responsible for the removal of biogenic material and solids through the rapid sand filter.
As we move forward in a world of growing water demand and shrinking water access, it has become increasingly critical for us to take particular care in how we use our water sources. Water is taken up by many industries across the globe, and as these industries grow, so does their water utilization and supply requirements. This problem has become increasingly exacerbated in arid and desert-like regions, where already scarce water supplies have become increasingly strained by the increase in demand. In exploring the use of water for power plants and their cooling needs, we sought to find possible optimizations of water use, particularly in evaporative cooling towers.
Cooling towers cycle through millions of gallons every day, even on a small scale, meaning that there is a large capability for saving water over a considerate amount of time. If we can remove enough energy, we can save water by not having to vent it to the atmosphere, and we can use water to cool other parts of the plant once it has been cycled.
Our process design is comprised of a treatment train of multiple water purification unit operations, designed to limit the dissolved substances entering cooling towers. The five primary methods of filtration selected for this process were sand filtration, reverse osmosis, ion exchange with demineralization specialization, as well as ion exchange with heavy metal specialization.
Our project called for a dry and arid climate so that we were saving water in the places that needed it most. The Rio Grande River had extensive well data, so it was a good fit for the feed water data when it came to the multiple power plants that use it. This allowed us to get a comprehensive look at the contents of the water and the ability to apply our treatments to many different cooling towers that use it in this area.
Through our research, we found a number of quantifications that make the Rio Grande power plant an ideal choice for this project, both in the supply of water it uses and the quantity. In our research, we found that the Rio Grande power plant draws in roughly 800,000 gallons of water every day. While this consumption of water is critical, it gives our project room for improvement as we seek to lower consumption. The rapid sand filter protects downstream unit operations from conditions adverse to their function and removes contaminants in the feed water. The filter primarily traps solids, biological foulants, and substances which would otherwise not be removed by the ion exchange process or not efficiently removed by the reverse osmosis process. The system utilizes a bed containing fine quartz particles which act as absorption sites onto which contaminants within the water may attach. Particles also physically block large contaminants, such as suspended solids and biofilms, from passing. As the filter is active, it will gradually accrue scale and hardness from the water. To prevent the media from becoming a solid mass due to the buildup of minerals in the pore spaces between individual particles, the system must engage in frequent backwash cycles to break up the media and remove any solids suspended in the water or attached to the media.
Heavy metals often have high heat capacities and low heat transfer coefficients, making them inefficient for absorbing and quickly releasing energy. This is undesirable in cooling towers. Removing these heavy metals requires both highly charged cationic and anionic resin compounds. This approach captures a wide range of heavily charged particles during the cleaning process while leaving other potential contaminants unaffected, helping to prevent scaling over time. As a result, the system can operate through multiple cycles without needing the frequent descaling that others might. This improves overall efficiency and allows other operations to handle the remaining contaminants. By distributing treatment and responsibilities across multiple processes, no single unit is overburdened.
Two of the biggest driving factors in our water-saving quantifications is the total dissolved solids and total hardness present in the water being fed into the tower. Ion exchange is an exceptionally capable process for the removal of these solids, and in particular dissolved salts and chlorides. The ion exchange process is capable of targeting both positively charged cations and negatively charged anions present in water supplies, allowing for the mass removal of our most targeted materials. When water comes into contact with a specialized resin housed within ion exchange tanks, it exchanges contaminants with more desirable ions on the surface of the resin. Over time, the resin's surface can become full, losing its purification abilities and requiring regeneration. This regeneration is done with a brine that takes back in the undesirable ions and resupplies the desired ones.
Reverse osmosis is a pressure-driven membrane process that removes dissolved salts and impurities, producing a clean permeate stream and a concentrated brine stream. The system is designed as a two-stage configuration, operating at about 70% recovery. The first stage handles the full feed, while the second stage processes the concentrate to recover additional permeate. The system uses spiral-wound thin film composite membranes, specifically the BW30HR440i, selected for its high membrane area, strong salt rejection, and suitability for brackish water. Overall, the RO unit enables effective water treatment and reuse within the system. To design and evaluate our treatment system, we used DuPont Wave, an industry-standard modeling tool for membrane and ion exchange processes. The software allowed us to simulate performance under varying conditions such as flow rate, pressure, and feed water composition, while predicting outputs like permeate quality, recovery, and waste generation. We initially modeled a wide range of configurations, running 16 different permutations that included ion exchange, dealkalization, ion exchange softening, reverse osmosis, and sand filtration. This comprehensive approach helped us evaluate both treatment effectiveness and system costs. From these simulations, we determined that a full 4-stage system was unnecessary. While we developed and analyzed a 2-stage RO design, our results showed that a simpler configuration could achieve comparable performance. The optimal setup uses sand filtration as pretreatment to remove suspended solids, followed by ion exchange softening to address hardness and prevent scaling.
Water savings are critical to the goals of the project as a method of conservation both for businesses and for the region's water supply. In the course of project development, a large disparity has been found between the water lost during the various processes and the water saved during the evaporation process. The magnitude of water that is needed in the evaporative cooling towers is monumental, and the amount of water rejected from the circulating system over time is dwarfed by the volume of water evaporating from the system. Using an analysis of both the total hardness of water and the total dissolved solids entering a cooling tower, an estimate was generated for the theoretical possible savings of water in cooling towers of various sizes, shown here and here. Because of the methods used, the greatest quantity of water that can be saved is the total water that is rejected. In comparison to this, the amount of water treated for the cooling tower influent supply is far greater. But what does this mean for our project? This is an indication that the water filtration process must reach high levels of water recovery. Calculations indicate that any break-even point for water saving requires recovery levels of 99% or greater. Given that most water filtration systems are unable to reach these levels, this indicates that the system will result in a net loss of water. This is particularly apparent after seeing the results presented by Wave. Under these permutations of technologies, by using an analysis of total dissolved solids, the most optimal system was found to be the solo operation of ion exchange softening, resulting in a net loss of 14.5 million gallons of water annually.
In order to evaluate project success, metrics were created to determine the efficacy of the project. The treatment cost of the overall process and the water saved by the process are both used to benchmark the system and determine if the project can be considered successful. Cost is measured in the future dollar value of the project as a function of the combined investment costs and annual operating expenses of each unit process evaluated for a 13-year project lifetime. Water saved is evaluated using the cycles of concentration, a metric which represents the ratio of dissolved solids in recirculating cooling tower water as compared to the source water. A more effective process results in higher cycles of concentration. Profitability of the system was considered to be secondary in importance to the quality of the water produced by the system.
The project's capital costs are orders of magnitude lower than the long-term operating costs, as they are limited primarily to the construction and material expenses associated with building the treatment units. Before adding the continuous costs of operation that come from labor, chemical purchases, waste disposal, and water costs, the capital cost of the water treatment system totaled up to around $21 million, indicating the need for large yearly revenue. Furthering this conclusion, the yearly costs of operating the system over a 13-year period total a net loss of $77 billion. Through these findings and computation and optimization, we have determined that the feasibility of this system is entirely non-existent, both by the measure of the water saved and the cost of the system. The water saved by this method presents a large problem. After further analysis, the quantity of the water that is lost due to evaporation is magnitudes larger than the quantity of water lost due to rejection in the form of blowdown water. For this method of treating water prior to use in the evaporative cooling tower, we can lose between 7 and 28% of the initial water. This loss during treatment ultimately dwarfs the savings, which present themselves as a lack of rejection water. This leads to the economic infeasibility of this project, as the system would have to cost billions of dollars while actively increasing the use of water.